Ammonia is an important molecule for fertilizers, but that doesn't mean that it gets spread directly onto farmers' fields. First, it's made more stable and more easily absorbed by crops if it's reacted with nitric acid to produce ammonium nitrate, an ionic compound composed of positively charged ammonium ions and negatively charged nitrate ions. Ammonium nitrate can form several different crystal arrangements, and it's subject to several different decomposition reactions depending on the conditions. Before ammonium nitrate can be used as fertilizer, it must first be dissolved in water. It's highly soluble, but it takes some energy to get it to decompose into its ions. The energy for the reaction comes from heat in the environment, so the reaction container feels cold to the touch. You might have felt this yourself if you've ever used a chemical cold pack. Chemical reactions that extract heat from the environment are called endothermic reactions. The opposite type, exothermic reactions, release heat into their surroundings, and some ammonium nitrate decompositions fall into this category too. On its own, ammonium nitrate is not flammable, and it's insensitive to all but the most extreme shocks. But at high temperatures, equilibrium starts to reverse the formation reaction and produce ammonia and nitric acid. Through subsequent reactions, the nitric acid breaks down into nitrogen dioxide. Nitrogen dioxide gas has a distinctive red-brown color commonly associated with highly concentrated nitric acid, otherwise known as fuming red nitric acid. Where does the oxygen for these kind of reactions come from? The concentration of oxygen in the atmosphere is too low to support a continuous reaction. However, ammonium nitrate can become its own source of oxygen during detonation, where it undergoes a different kind of decomposition reaction. Real detonations release so much energy that they generate a much larger range of molecules and ions than is shown here. But this simplified model lets us calculate an overall reaction which rapidly generates and heats 13 moles of gas for every 4 moles of solid starting material. The force of this expanding gas is what gives explosives their destructive power. And this is what we saw in the explosion that devastated the port of Beirut on the 4th of August, 2020. The expanding blast wave compresses humidity in the air, creating a spherical cloud. Then the rising pillar of red gas appears to be nitrogen dioxide, indicating pure ammonium nitrate as the source. If this had been a commercial explosive or military munition, the ammonium nitrate would have been mixed with some kind of fuel, either oil or wax, or even aluminum powder, to increase the explosive force and the energy released. It's the most common type of explosive used worldwide for mining and for demolitions because it's a stable, easy-to-handle solid. It's this same property that makes it so desirable for agricultural purposes, and why it gets shipped and stored by the ton. Also why it's implicated in some of the world's worst industrial accidents. It takes a large, uncontrolled fire to get it to detonate, but when that fire occurs, explosion is the predictable and disastrous result. So here we've seen an example of a single material, ammonium nitrate, that can decompose to cool and to heal, or to heat and destroy, to dissolve into a nourishing liquid, or to decompose into toxic gases. Those gases can also have secondary effects as they expand and cool, effects that we'll begin to discuss in our next video.